Okay, welcome to the video on sort of more properties of radiation. In particular, we're going to be talking about gamma and the inverse square law of radiation. We're going to look at some experimental results. But first, just a little bit more background on alpha, beta and gamma. Alpha radiation. Originally, Rutherford was investigating what alpha radiation actually was, and he collected alpha particles that were being emitted from a particular source, or what he didn't know was alpha particles, but he collected them into a glass tube, and he realised or he noticed if he applied a high voltage across them and the gas conducted electricity, the light emitted could be analysed using by spectrometer, which you've looked at in year 12 and worked out that the emission lines were from helium, so hence deciding from the evidence that alpha radiation must be helium. So, you know, a little bit of a story here. We've got the alpha particles. Once we found out they were helium, this was the lightest known atom at the time, was hydrogen. So helium was different to hydrogen. That hydrogen was a single charged positive particle, and this was afterwards named the proton. Helium was different to it because it was twice the charge but 4 times the mass. So the idea being that it's got 2 protons, but as we mentioned in an earlier video, it had 4 times the mass, and from this the neutron was predicted and later established. In that we mentioned that back in the first video in this little series on radioactivity. Beta radiation, fast-moving electron. This was worked out by comparing specific charge data already established by the electric field acceleration, etc., in a magnetic or electric field. So there's enough data there to work that. Gamma radiation, using diffraction experiments, again talked about in year 12 slightly, with a crystal to diffract a beam of gamma radiation and getting similar results to light diffraction, showing that gamma radiation must be part of the electromagnetic radiation, and from the diffraction pattern you can work out the wavelength, and this must be in the order of 10 to the minus 11. So you can sort of see how some of this starts to join up with the physics that you've done in both year 12 and year 13. Okay, on to the main idea for today. If we were to investigate gamma radiation, how could we do this? So a little simple picture here. We would effectively have a Geiger monotube, and we would have a radioactive source, and if we varied the distance between the source and the Geiger monotube, we could get some readings of count rates at different distances to maybe work out if this is an inverse square relationship. So basic instructions: use the GM tube, take a background count over a particular time, and again you could, if you had lots of time, you could do this over 10 minutes, 20 minutes. The data I've got I think is based over a minute. Set up the gamma source close to the GM tube, but not so it is overwhelmed with activity. In the last video we talked about the dead time of a GM tube when it becomes overwhelmed, so not too close. Measure the distance from the GM tube to source, try about 5 centimetres. Obtain an average count for this distance, and again you could do this for a particular time. Repeat over a wide range of distances, maybe every 5 centimetres. Does the inverse square law apply? How can we tell? Okay, so just things to think about. What should happen to the count rate if you double the distance? And if it's inverse square, remember doubling the distance will quarter the count rate. Could we prove this graphically, maybe using a straight line graph? And the other thing to think about is, how do we actually know how far we are from the source? In this particular picture, what are we measuring? If we just measure this gap, is that the distance between the source and the counter? I mean, where is the centre of the source and where is the centre of the counter? So this could be a question on the practical part of the paper. Okay, so let's have a look at some very quick data. Here are my distances, so 5, 10, 15, 20, 25, 30, 35, 40 in metres, so centimetres, so in metres 0.05. I've got a count rate per minute. And then we've got an adjusted count rate. The adjusted count rate here per minute, what we've done is just taken off background count. So hopefully you can see that it looks as though my background count was 85, 90, about 13. So each of these are 13 lower. Okay, so difficult to plot a graph using just straight data like this. If we were looking for an inverse square, we'd be looking for some kind of a curve. It is better to have a straight line graph, so let's just consider what graph we could plot. If we've got a prediction that the intensity does vary with inverse square of distance, we can see that the intensity is proportional to 1 over the distance squared. that's exactly what we mean by an inverse square. We'd have to have some kind of a constant in this equation to get rid of the proportional and put in the equals. So the intensity here equals to some kind of a constant divided by the distance squared. And here, this K would actually involve the intensity at the source, the original intensity IO. There might be some other things in there, but that would definitely be the constant, would involve whatever the intensity of the radiation of the actual sources. So you could read, this is the one you give on the formula sheet, but I sometimes like to put this K separate to IO, so you know that the original intensity of the source is going to be part of that. Okay, we've definitely, like we're doing in our data, we've got to adjust I for background, but our problem is X is quite difficult to work out because we don't know the distance to the source. So again, just putting in here a little correction, we've got I is equal to K over, in brackets, X plus XC all squared. So what I'm suggesting here, that we've got an extra bit of distance. X is the distance that we've measured between the source and the cat and the GM tube, and really that isn't correct. We've got another little bit, if you like. We've got an extra little bit of distance that we need to bring in because we don't know what this XC is. It's difficult to measure the exact distance. Okay, so if we square root both sides, let's have a look what we can do to this. So root I equals root K over X plus XC. So I've just square rooted I, square rooted K, and square rooted X plus XC squared to give us X plus XC. Just rearrange it. If we bring the root K down here, so root I over root K is equal to 1 over X plus XC. Just inverting it, so root K over root I instead of root I over root K. So inverted this side, inverted the other, and then we're left with, to get this in the form of y equals mx plus c, I've just moved over the xc here over to this side, so to give us x equals root k over root I minus xc. So now we could plot on a graph, we could plot x is equal to, on the x-axis we could plot x, which is the distance, and on the y-axis, if we plotted 1 over root I, okay, 1 over root I, that will give us hopefully a straight line graph with an intercept of xc and a gradient of root k. So here we have our equation, x equals root k over root I minus xc. Let me just show you that slightly different in terms of where the root k is. So I've just moved the root k over, so now I've got 1 over root I, the intensity. So here you can see y equals mx plus c. Okay, so if we plot a graph of distance on the x-axis here against 1 over root of the intensity, 1 over the root count rate here on the distance on the y-axis, forgive me. So if we plot distance on the y-axis here, it's confusing because it's x, distance on the y-axis here against 1 over root I on the x-axis here, we have a gradient of root k and intercept of xc minus xc, and bearing in mind we're more interested here in finding our offset in the intercept, or our offset in the measurement. Here's our data that we had on the previous slide, and I've just done I to the half here, so there's our adjusted count rate, I to the half, and then done 1 over I to the half, and I've plotted this first column D against 1 over I to the half, this last column here. That's given me a graph. You can see it's fairly straight. I've used Excel just to do a line of best fit, and you can see we have got a slight negative intercept on the y-axis, and this is 0.0102. So we are saying that xc minus xc is equal to minus 0.01. So from that, the minuses cancels. We would say that we've got a corrected distance in our distance between the source and the tube of about 1 centimetre. And if you think when we did the practical in the lab, that doesn't seem too far away. And the other thing to remember is why we did all this was to show that the relationship between the count rate and the distance is indeed an inverse square relationship. And remember, our graph is straight. I know we've just used the intercept, but fundamentally the graph is straight. So because this is a straight line, this means that the relationship is an inverse square. Bearing in mind what we started off, how we got this equation, we did some maths with the original. If I just skip back, you'll be able to see all of the maths that we did here. If you remember on this slide, all of the maths here started from the assumption that it was I equals k over x squared, and then we just did a little bit of maths to end up with our final equation that we have just plotted against, and because it's straight, we have therefore proved that it is indeed an inverse square relationship. Okay, so how would we apply this in practical terms? Very often you do not know the intensity of the source, but you have two count rates. So you might have I1 and I2 at two different points of distances x1 and x2 from the source. So using this idea, we've just got two equations. This is I1 at x1 and this will be I2 at x2. So if we just divide these two equations, okay, there you go, I1 over I2 is equal to I1 over I2. Obviously the constant and the intensity of the sources just cancels out, so we end up with I1 over I2 is equal to x2 over x1 all squared. So this is the intensity at distance 1, this is the intensity at distance 2, and this is the distance 2, and this is distance 1. This isn't on the data sheet, but it's very often used in calculation, so it's worth remembering. And this, as I say, enables us to work out an unknown intensity at a particular distance, or a distance where a particular intensity occurs. Quite useful if you don't want to get too close to a radioactive source. So we've got some quick questions. A sample of radioactive isotope emits 1.2 times 10 to the 12 gamma photons per second in all directions. Assuming that the area of a person is about 1 meter squared, estimate the number of photons per second received by someone standing at 2 meters, 4 meters, 5.5 meters from the source if they were accidentally exposed. So here we go for part A. At 2 meters, we've got the radius of a sphere at 2 meters from this center point where the source is would be 4 pi r squared. So 4 pi 2 meters squared to give us an answer of about 50.27 meters squared. Now the person standing received the area of the person in the question, it says, is about 1 meter squared, so they are receiving this fraction 1 over 50.27 of the original dose, so they're receiving 0.0199 of the original photons being emitted, 1.2 times 10 to the 12. So you can see I've done this fraction of the original will give you their actual dose per second, so you can see it's 2.39 times 10 to the 10 per second in terms of the photons hitting them. Part B, what happens? Well, if we double the distance, 2 meter goes to 4 meters. As our graph earlier, it's a straight line, so it shows that this is an inverse square. So 2 meters to 4 meters, if we double the distance, we quarter the radiation. So double the distance, intensity reduces by 4, so just divide our previous answer by 4 to give us about 6 times 10 to the 9. Part C, you can do this different ways. I'm just going to show you how to use this equation at the top, I1 over I2. So here we've got the equation I1 over I2 equals x2 over x1 all squared. Let's feed our numbers in. We've got I1, this intensity, 2.39, was at 2 meters, so this is at that distance. And then we've got the intensity at 5.5 meters. We don't know here, so I've left that as I 5.5, but here is the distance of 5.5. So we've just got 4 bits of the equation, 3 of them are known, 1's unknown. Just do some maths, solving it, rearranging it, and you get an intensity at 5.5 meters of about 3.16 times 10 to the 9 per second. Okay, another question. If the area of a detector is 4 centimeters squared and it reads 100 counts per second at 10 centimeters, what is the total output from the source? So this is quite useful, that we want to know if we're at a particular distance, we're at 10 centimeters and we're receiving this count, then it would be nice to think, well, what is the actual output from the source? Okay, so the area of the complete sphere at 10 centimetres is 4 pi r squared, 4 pi times 10 squared, which is 100. So the area of our sphere is 1,256 centimetres squared, and we know from the question that the detector has got an area of 4 centimetres, and that's picking up 100. So what we've got to do is work out how many 4 centimetres are in this value. So if we do 1,256 divided by 4, and that fraction there or gives us an idea of how many detectors worth, if you like, how many 4 centimetres squared are in 1,256. So, and at that we get an answer, multiply that by 100, and then that gives us a total count rate of 31,400 counts per second. So again, not using the main formula, but just using the idea of ratios. Question 3, a detector placed 0.2 metres from a sealed gamma ray source receives a mean count rate of 2,550 counts per minute. The mean background radiation count is 50 counts per minute. The experiment is set up as shown, so similar to what we've done, we've got a detector and a source measuring this. Measuring from particular distances. Calculate the least distance between the source and the detector if the count rate is not to exceed 6,000 counts per minute. First thing we need to do is correct some of the count rates to bring into background. So the corrected count rate at 0.2 metres is going to be 2550 minus 50, which is 2,500, and the corrected count rate at the new unknown position, which I've called it, is 6,000 minus 50, which will be 5950. We can then use our equation. Okay, so we've got intensity of 2,500 at 0.2, and we've got an intensity of 5,950 at an unknown distance x, and I've just called it x subscript 5950. And again, solving that, shoving the numbers in and doing our little bit of maths, you should get an answer of 0.13 metres, and this makes sense as 0.13 metres compared to 0.2 metres, so we've gone closer to the source and our count rate has indeed gone up.